I'm hoping to tell you the story of the discovery of gravitational waves, which was predicted by Albert Einstein exactly 100 years ago in 1916. And this recent discovery of gravitational waves is important not only because it confirms a century-old prediction of Einstein, but it essentially opens up a new branch of observational astronomy, a new way of observing the universe. So essentially, soon after discovery, it captured popular minds all over the world, and it really became part of the popular culture. It even made it to the Amul advertisement. So I saw this billboard in Mysore, which reads "All but Einstein." It shows the popularity of gravitational waves of regained recently. So let me start by showing a few pictures of the universe that we obtain from different branches of electromagnetic astronomy. I suggest that you look at those slides, that projector, because that is better quality. So, of course, if you look at the sky using an optical telescope, you see a familiar picture of the optical sky, the stars, galaxies, and so on. And essentially, it's dominated by our own galaxy, the Milky Way. But if you look at the same sky using a detector that can detect microwave radiation, you get to access to a very different history of the universe. What you see from everywhere in the sky, a cosmic radiation, a radiation coming from a very early universe called the cosmic microwave background radiation. It's shown in this middle panel, this with red and blue regions. So essentially, the radiation comes from an age of the universe when it was very, very young, and it's only about 100,000 years old. And we know that now the universe is about 13 billion years old. So it's a baby picture of the universe. And you see here in this top middle panel some blue regions and red regions. This shows the temperature of the cosmic microwave region of background radiation. And of course, this temperature difference is extremely minute. But this red regions eventually became stars and galaxies, and these blue regions became essentially large intergalactic voids. So similarly, if you look at the sky using an X-ray telescope, you get to see very high energy phenomena involving black holes accreting matter around them, very high energy neutron stars, etc., etc. So it's fair to say that essentially all the information that we gain about the universe mostly come from astronomical observations of electromagnetic waves. But recently, astronomical observations using non-electromagnetic messengers also have become possible. This plot shows the arrival directions of very high energy neutrinos. Neutrinos are subatomic particles that are chargeless and almost massless. This is observed by a fantastic observatory in Antarctica called the Ice Cube. These have very high energies, hundreds of GeVs, and it's not entirely clear what is producing them. This is rather reasonably clear that it's coming from extragalactic sources, and it shows really how a new branch of astronomy opens up new questions. And the neutrinos and electromagnetic waves contain very complementary information. For example, electromagnetic waves are produced by the surface of objects, stars, or their atmosphere, etc., while neutrinos are typically produced in the interior of these objects, in the interior stars due to nuclear reactions, etc. So they essentially contain information contained to very different physics. So by combining this information from multiple messengers, we are able to provide a more complete picture of the astronomical source that we are probing. And finally, I would like to show the first picture of the gravitational wave sky. This is the reconstructed location of the first gravitational wave signal observed by LIGO last year. This is produced by a merger of two binary black holes. Before I come to describing this discovery, let me give you a very brief introduction to what is gravitational waves are. So the existence of gravitational waves was predicted by Einstein's theory called the general theory of relativity, which is already celebrating its 100th anniversary. So this GR, general theory of relativity, is the most accurate description of gravity available to us now. It is much more accurate than the Newton's theory that we all study in school. Essentially, it tells that gravity is nothing but the curvature of space and time. It's a single entity called space-time. So if you have any massive object, like an apple, it curves the space-time around it. So of course, the the space-time curvature produced by an apple is extremely small, but if you have a really massive and compact object like a black hole or even the sun, it produces a significant curvature of space-time around it. And of course, very far away from the source of gravity, gravitating source, the curvature is very, very small. So it's a very, very approximately a flat space. So if you, for example, all the usual axioms of Euclidean geometry holds in this flat space. For example, if you draw a triangle and sum the angles, you get 180 degrees. But if you do the same exercise in the vicinity of this massive object, this axioms of Euclidean geometry does not hold. For example, if you draw a triangle and sum up the angles, it will no longer be 180 degrees. So the space-time is truly curved there. And so it might look like a very exotic and prediction, but we are already using the predictions of GR in our daily life. For example, most of us have smartphones and we use GPS to navigate in the streets. So if the GPS has to work, the effect of the curvature of time, the effect of the slowing of time due to the gravity of the earth has to be taken into account, because essentially GPS uses a system of very precise clocks to essentially locate our position in the three-dimensional space. And the point is that clocks tick at different speeds depending on their gravitational field. So a clock that on the surface of the earth would tick slower than an identical clock that is on the outer space. And just since GPS relies on clocks that are placed on board satellites, essentially one has to take into account this minute change in the flow of time for the GPS to work accurately. And gravitational waves are something more exciting, more exotic, that is predicted by Einstein theory. Essentially, it tells that I told you that a massive object curves the space-time around it, and when this massive object moves, the space-time curvature moves with the body. And when this moves with an acceleration, this oscillation in the space-time curvature decouples from the source and propagate outward like ripples in space-time. So gravitational waves are freely propagating oscillations in the fabric of space-time, which is as shown in this animation, which is produced by, which shows a gravitational waves produced by an orbiting binary star system. Now, how do you detect gravitational waves? When gravitational waves pass through the earth, they produce some very characteristic deformation in the space, the spatial metric. So, for example, if a gravitational wave is passing perpendicular to this board, one direction of space gets stretched and the other direction gets compressed. So it's characteristic of what is called tidal forces. For example, tides of the earth created by the moon. For example, the earth has a really fairly spherical shape, and due to the gravity of the earth, it gets deformed into ellipses. The gravitational waves does something very similar, but except that this deformation is perpendicular to the direction of propagation of this wave. So this space is stretched and compressed in the direction that is orthogonal to the direction of propagation of this motion. It's shown in this nice animation. You can see that if you arrange a ring of particles, that are test particle that allows to move freely according to the stretch, strain on the space. If you arrange it in a circle, then the circle gets deformed into ellipses, and this deformation propagates outwards at the speed of light. This is called gravitational waves. And there are different ways of detecting gravitational waves that have been proposed, and the first successful one has been using what is called laser interferometer. So we will hear about this instrument that made this detection of gravitational waves in the following talk by Bala Iyer. But essentially the idea is that uses something called a Michelson interferometer, a very sophisticated Michelson interferometer. This Michelson interferometers have been around for more than a century. It's a very standard technique in physics. But the problem is that the expected change in the space, expected deformation of the space, as well as the expected change in the arm length of this interferometer is extremely tiny. So the fractional change in the length of the space or the length of an interferometer is of the order of 10 to the power 21, even for a very loud source that, for example, like the one that we observed for the first time in LIGO. This means that if you are using even a kilometer scale detector, an interferometer that has a kilometer's arm length, it should be able to detect extremely tiny changes in its arm length of the order of 10 to the minus 18 meter. And that's a huge experimental challenge. And by far, these are the most these instruments are the most sensitive measurements for measuring length ever constructed by humankind. We will hear about this in the following talks. And an international network of such detectors existed in the last 10 years in the US, Europe, and in Japan, etc. And the first generation of these detectors have been conducting a data taking runs over the last 15 years or so at various times, but they were not successful in making detections. But these LIGO detectors in the USA essentially underwent a major upgrade in the last few years to a configuration called advanced LIGO, which was much more sensitive than the previous generation of LIGO instruments. And as soon as they started operating on the 14th of September 2015, they detected the first gravitational wave signal. In fact, this was actually before the official start of the scientific run. Thus, these gravitational waves were waiting for us. So these two signals arrived in these two detectors at a time difference about 7 milliseconds, because they travel at a finite speed, at the speed of light. And the combined signal to noise ratio, this is a very loud event. The combined signal to noise ratio of this event was of the order of 24. The signal was about 24 times larger than the noise. And these gravitational waves have frequency in the audio frequency band. They have frequencies of the order of 10 hertz to a few kilohertz. This is the frequency where our ears are sensitive. This is called, that's very called this audio frequency band. So it's actually possible to convert the observed signal into a sound and play it in a loudspeaker. And I will do that now. I'll show this observed signal, and you can actually listen to this signal. Because the buzz that you heard is the instrumental noise, but you see like a ploop and ploop. This is the sound of the first gravitational signal that we observed. And this plot shows the observed signal in the two detectors. The horizontal axis is the time so it's only a fraction of a second, it's of the order of 0.1 second. And the vertical axis shows the amplitude of this oscillation as a function of time. Suddenly these detectors were oscillating as a function of time with this frequency. So you see this characteristic singular shape that we were expecting to observe using which correspond to the merger of two black holes. And also this shows how the frequency of the signal increases as a function of time. It starts from low frequency, go to very high frequencies. So by the careful study of the observed signal, the collaboration has concluded that this is consistent with a signal expected from the coalescence of two black holes. That is, two black holes formed at some distant galaxy as a binary system. They were orbiting about each other. They lose energy into gravitational waves, and as a result, they come closer and closer. And as a result, they rotate faster and faster. And eventually, this becomes like a runaway process, and these black holes merge to form a common black hole, a common horizon, and which settles into a single rotating black holes. And this is the expected signal from such a phenomena that you can compute by solving Einstein's equations in general relativity, and the observed signal agrees very well with this prediction. So the signal has a very characteristic shape. If you look at the earlier part, it has an increasing amplitude and increasing frequency. Such a signal is called a chirp, because the spectral characteristic of this signal is very similar to the chirping of birds. So it's called a chirp signal. And the later part, when these black holes merge, essentially the signal amplitude dies as exponential. So this discovery is what physicists call a 5 sigma discovery, which is like a gold standard for detecting anything new in physics. This means that essentially it's extremely unlikely for anything other than a gravitational wave to produce a signal like this in our detector. The false alarm probability, the probability that something other than a true gravitational wave to produce something like this signal is less than 10 to the minus 7. It's extremely unlikely. So, or in other ways, it's only once in 2 lakh years, 200,000 years, you expect to see something like this produced by noise. So we are pretty short, very extremely certain. We are very confident that this is a true gravitational wave signal. And it actually took a lot of time to establish this with this confidence, because if you remember, the signal was discovered on the 14th of September 2015. So, and the detection was made 3 minutes after the signal arrived in the detector. But this discovery was announced only in February 2016. So in this 5 months, all this 1,000-member collaboration was essentially doing an extremely exhaustive exercise to make sure that this is indeed a gravitational signal. Essentially, thinking of all kinds of possible alternative explanations and ruling them out. So what are the possible explanations, alternative explanations? For example, there are, this detector is operating in our environment. So in principle, various environmental noises such as seismic events or magnetic events, etc., can cause an event in the detector. So in order to make sure that this is not caused by any of the environmental or instrumental noise artifacts, there are essentially thousands of sensors, seismometers, magnetometers, microphones, acoustic sensors, etc., placed around the instrument, as well as the detector is monitored by around thousands of ports. So there was an exhaustive exercise to make sure that this data could not be explained by an event in any of these environmental channels. So we find absolutely no evidence that this could be an instrumental artifact, because none of the environmental sensors recorded an instrument and determined that can potentially couple to this gravitational wave event channel. We also essentially explored the possibility of someone either maliciously injecting something, a signal in the data, and this was also ruled out by a large amount of human exercise. So we are fairly confident, we are extremely confident that this is a true event, and this is one of the most, in fact, this is the most powerful astronomical source ever observed by humankind, because about 3 solar mass worth of energy has been converted into gravitational waves over the course of a fraction of a second. Using a 3 solar mass of energy, an equivalent of 3 solar mass of energy in terms of mc square is converted into energy and radiated in a fraction of a second. So if you convert the power emission from the source during this merger, it's of the order of 10 to the power 49 watts. Which, if you imagine, it is 50 times larger than the average luminosity of all the stars in the universe put together. So if this, for example, if this event was converted into, this energy was converted into electromagnetic energy, it would sort of outshine the entire universe. But this was not converted into light. There was no light emission. All this energy was converted into gravitational waves. And because the gravitational waves, gravity couples to matter extremely weakly, even with such a large explosion of energy, this observed signal is extremely feeble, and it takes this huge amount of effort to observe such a signal. So by studying the data, by comparing this data with theoretical predictions of this source by solving Einstein's equations, we conclude that the signal was produced by the merger, the in-spiral and the subsequent merger of 2 black holes with masses 36 and 29 times the mass of the sun. These are extremely massive black holes. And they merged to produce a single black hole of mass 62 times the mass of the sun, even more massive black hole. It was rapidly rotating, that is rotating with a spin, a dimensional spin, is of the order of 60.667. So they were spinning the 67% to the maximum spin possible in a curved black hole in general relativity. So those who are careful, you might notice that the mass of the final black hole, 62, is smaller than the sum of the initial masses, which should be 65. So this 3 solar mass of mass is converted into energy in this process. And a second signal was detected on the 26th December 2015. This was produced by the merger of a lighter black holes of masses 14 solar mass and 8 solar mass, and they have merged to form a remnant black hole of 21 solar mass and the spin of 0.74. This observed signal is entirely consistent with the prediction of Einstein's theory. So in fact, it's a remarkable test of Einstein's theory. It's the first test of Einstein, this provides the first observational test of Einstein's theory in the highly relativistic regime. So before these black holes merged, they must have been traveling at a speed just close to the speed of light, like 0.5 from the speed of light. So this is the first test of, this gives the first experimental verification of Einstein's theory in this extremely relativistic regime. So of course, Einstein theory passes the test with flying colors, yes. But of course, at this point, our errors are largely dominated by our statistical errors because we have large uncertainty in measuring parameters, etc. But one of the things that we hope to do using the future observations of gravitational waves is by combining a large number of observations to make very, very precise constraints on deviations of Einstein's theory, etc. Even this first observation of gravitational waves also has a profound impact of our understanding of astrophysics. For example, this is the first time we are detecting a new class of source which are a binary system of two black holes. The first time we are seeing such source by any means of astronomy. And in addition, this first event, the black holes involved in this event, masses about the order of 30 solar mass, were significantly more massive than the mass of black hole that people thought would exist in the universe. Mass of stellar mass black hole, that are black holes produced in the collapse of massive stars. So most of us were believing that the stellar mass black holes would be less massive than of the order of 20 solar mass. So the first time we are seeing stellar mass black holes with mass more than 25 solar masses. And by making use of this observed number of events, in fact, a third less significant event was also discovered in October last year, but we don't call it as a confident detection. So still, by studying this, by making use of this observed rate of gravitational events observed by LIGO, we can make predictions of the rates of compact binary coalescence, the rate of the mergers of binary black hole systems in the local universe. And we expect that by means of this observation, we expect that every gigaparsec cube of the local universe would have of the order of 9 to 240 binary black hole mergers to happen every year. This means that if you continue operating LIGO with improved and improved sensitivity, you will see several more signals in the next few years. And when the LIGO observe in its design sensitivity, you are expecting to see hundreds of binary black hole mergers every year. So this is going to be opening a completely new branch of observational astronomy. So because of this large number of astrophysical sources that are merging at the same time, we expect what is called a stochastic background of gravitational waves produced by this large number of astrophysical events. And this is something that we are very, very excited about, and we hope to see such a background, a gravitational wave background in the next 5 to 10 years. And Ajith here is an expert on detecting such a background. And hopefully we will talk about more in this little bit. So let me conclude this talk by essentially juxtaposing the sky that we have observed in gravitational wave window on top of this all these observational windows that existed prior to the LIGO event. So of course, so this is the reconstructed location of the first LIGO event that we reconstruct using the data. And of course, we don't have a very precise location of the source. So we can see that the signal must have come from a large patch in the sky, shown by this colored contours here. And this is because gravitational waves have a very different characteristic. Their detectors work in a very different way. They are very different from a telescope, which you can point to a particular point in the sky. They are essentially antennas that has large antenna patterns. So essentially, if you have one detector, it can basically able to see almost gravitational waves coming from almost everywhere in the sky. So the way we localize the source in the sky is by combining the data from multiple detectors that are geographically separated, by looking at the time of difference in the time of arrival of the signal at multiple geographically separated detectors. So the accuracy with which we can localize the source depends on the baseline of this international network, how far these individual detectors are located. And with this current LIGO detectors, the accuracy is not that good. So we are expecting to see several new detectors coming up in the next few years, but most importantly, we are expecting the LIGO India will come online in the next 10 years or by 2024 or so. And this detector is located at a significant difference from all these existing detectors, which will significantly improve the accuracy with which we can localize sources in the sky. And this is very important because we also want to see if this merger process, like the merger of neutron stars, etc., produce some electromagnetic counterparts also. Because if you want to do multi-messenger astronomy, you want to observe the same source using multiple means of astronomy. And LIGO India would be, in some sense, really the facilitator of multi-messenger astronomy using gravitational observation. And we will have a whole talk by Sanjit Mitra at the end of the session on LIGO India and the capability of the Indian detector for the future of gravitational astronomy. So I will stop by flashing a quote from Kip Thorne, who gave a plenary talk in the first day of the Science Congress. He was one of the founders of LIGO. So Kip Thorne says that with this discovery, we humans are embarking on a marvelous new quest, the quest to explore the warp side of the universe. So thank you very much.